Good
actually,
afternoon.
good morning.
Yeah, for others, for us it's good morning.
Yeah. Shall we start?
I didn't get the last bit.
Okay. Hello everyone, and welcome to today's Future Ocean Forum. I'm Xianyao Chen from the Ocean University of China, and I majored in the physical oceanography. And I'm also the host of today's seminar. It's my great honor to have the senior scientist, Martin Losch, from the Alfred Wegener Institute of Germany. And I would like to take this moment to provide a brief introduction to Martin. Martin received his degree in physics at the University of Hamburg in 1997, and his PhD at the University of Bremen in 2000. After 2 years in the MIT as a postdoc, Martin joined the Alfred Wegener Institute for the polar and marine research in 2003. And in 2008, he became a research scientist at AWE. And his research interests, including the numerical sea ice and ocean modeling, ocean mixing processes, inverse method, and data simulations. And one of my personal experience with contact with Martin, I remember is during 2002 to 2003, and Martin finished one of papers on the data analysis of the low ADCP. I remembered I sent the email to Martin. At that time, I didn't know him. Yeah. And I just dropped an email to Martin to ask for his code. And I got his reply within 24 hours. That's amazing for me. I still remember this. And I remember in the next time when I visit the AWE, I mentioned this a small story. It's really important for me because I was just a young scientist during that time. And thank you, Martin. The theme of Martin's talk today is, do we need the non-Boussinesq effects in an ocean general circulation model for climate simulations? That's also one of the important topics because we know that there's the ice melting and the ocean thermal expansion in the context of the global warming. And our traditional models is Boussinesq approximations that keep the volume of the ocean water fixed. But some models use the mass of the ocean fixed. So that's called the non-Boussinesq effect. So I think these important topics, especially during this the warming period. So Martin, so let's welcome the Martin to give us this seminar.
Thank you very much, Xianyao. So I will now share my screen.
Yeah.
Okay. Does that look good?
Good. Go ahead, please.
I don't hear you anymore. Okay.
Can you hear me? Yeah.
Now I can hear you again, but
okay.
I can be heard. Okay, that's fine. Yeah, thank you very much for this very nice introduction, Xianyao. I was a very young scientist back then too, so just an exchange between peers, really. Yeah, I've always liked to interact with people from China, and I've visited China and also the Ocean University of China 10 years ago, so I think the last time, which I always enjoyed this very much. So thank you for that. Yeah, so my talk is about non-Boussinesq effects in general ocean circulation models, and actually do we need them for climate simulations? This is old work, but that I've been revisiting recently together with Jean-Michel Campin at the MIT. So again, this is a discussion that is 20 years and older, and there were a few publications that you can see here, especially Trevor McDougall and Greatbatch and Liu, who claimed that these these Boussinesq ocean models that we have are make serious systematic errors that we need to reconcile. And there was a series of papers that discussed these problems, and I actually had one contribution there together with Alistair Adcock and Jean-Michel Campin. And in these gray colors, I put the number of citations of these papers as of last year, about a year ago. Didn't update that yet, but I don't think it has changed much. You can see that this topic, even though it is important, does not receive that much attention, which is kind of weird. But I will still tell you that it is important because we can now measure mass quite accurately, and so the motivation for this discussion back then was that there was this satellite mission looming. Was supposed to start in 2005 or 6 or something like this, the GRACE Recovery and Climate Experiment. And this is a satellite mission that was set up to measure gravity very accurately. And with gravity, you could then estimate mass and changes of mass distribution of the Earth. And the new thing about this was that this was now super accurate. And the question is whether our Boussinesq ocean models that do not conserve mass but volume, as Xinya already said in the introduction, whether they are up to this and whether we can actually still use them. And the big question is back then was how can we test whether the difference matters. And this satellite mission GRACE was very, very successful. And it was so successful that there was a GRACE follow-on mission that is still flying today. So now here the image is of much higher resolution, but I think the satellite system is very similar, and this GRACE follow-on mission continues to measure the Earth and water movement and the surface mass changes, and so this is a very, very important ongoing topic. Okay, so I was told that this is that I should add a little bit of a pedagogical review here. So I wanted to start not with the Boussinesq approximation, but with the hydrostatic approximation. So because this, I will use this later on in the talk. So one of the assumptions here that we make when we set up our hydrostatic approximation is that the horizontal scale is much larger than the vertical scale of motion. So horizontal velocities are much larger, and then it turns out that the vertical acceleration that due to gravity can only be balanced by a vertical pressure gradient, and all other terms in the vertical momentum equations are unimportant. Here you see the full non-hydrostatic equations written for a coordinate system on the sphere. So this would be in latitude and longitude coordinates, and you have the 3 momentum equations. I wonder if you can see my pointer, I don't know, but you have these 3 momentum equations, and the first approximation that one can make is that the vertical acceleration is relatively small compared to the other terms that are the metric terms here and the Coriolis terms. So if we neglect these terms, and then there's some friction terms here, F. And if we neglect these terms, we come up with the quasi-hydrostatic approximation. It's still not hydrostatic, but because it still contains metric terms and second-order Coriolis terms. And then the full hydrostatic equation are these, where the metric terms vanish also entirely, and also from the momentum equations in the horizontal. And these are the hydrostatic equations that we usually use in ocean circulation models. Okay, and the important part is here that in the third equation, the acceleration due to gravity G is balanced by the vertical pressure gradient. There are no other terms in the vertical loss, and there's no acceleration in the vertical. For the Boussinesq approximation, this is a slightly different beast. has two parts traditionally. One part is that all changes in density are not related to the flow, but they're only related to thermal or haline effects. So that means if we compress the water, it doesn't have an effect on the density. That's the assumption. So that makes the first equation down there decouples the rate of change of density from the convergence or the divergence of velocity, so that we have incompressible flow, right? And this is what basically makes the equation no longer mass conserving but volume conserving. And the second term is that we replace the second part is that we replace all density variables in the equations where they are not coupled to the vertical acceleration. We replace them by a constant reference density, and this is this rho naught in the second equation. And so this allows lots of simplifications, but it also has consequences. And the most striking one is the following one, maybe, where we have where I integrated now here the continuity equation, the fully Boussinesq, non-Boussinesq continuity equation, and I marked the term that we are going to neglect in blue. And it's integrated from the bottom of the ocean to the surface. And then the only thing that can change this integral is the surface freshwater flux, which is this QFW, and this is divided by some constant freshwater density. But to have the units, and if you can then work on this integral and do all sorts of substitutions, and if there's time, I can show this in the end. But if you then average this over the entire domain, and this is the small bar or the over bar here in the second line, then you come up with an equation for the mean sea surface height or sea level, mean dynamic sea level eta, and this is then the averaged freshwater flux at the surface, or the mass flux or volume flux at the surface, and minus, and this is now this expansion term that is this is the Boussinesq or the non-Boussinesq effect or contribution to sea level change. So from this, you could immediately say that any sea level study, that should actually use non-Boussinesq models, because otherwise you make a serious mistake here, and you just totally neglect the expansion of due to warming or the haline contraction due to salinification or so. And but there's a way out, and this is what people have been doing most of the time. The global sea level can actually be very accurately recovered by a fix that was introduced by Richard Greatbatch in 1994. And so you have an actual additive correction to the mean sea level that is written down at the bottom. This is depends on the ratio of the mean current density of the ocean model divided by the mean density or some reference density at usually the mean density at the beginning of the simulation. So with this simple addition, you can fix your mean sea level, and you can use Boussinesq models that actually neglect the terms marked in blue, and you can use them and still have relatively accurate sea level changes in these models. Okay, that's on the global scale. More locally, you can, and this is now an image that I took from Wang and Jin from 1990, from a 2002 paper. Locally, it's more complicated. So think of, when you think of the real ocean, which is, schematically depicted in the top row figures, and you imagine you have this ocean warms locally. So you have, some area that is being warmed by atmospheric forcing, and then of course it expands, right? And so on the sea level changes locally, it rises. Then there's a sea level gradient next with because it's now different to the area around this local warming patch, and the sea level gradient is a pressure gradient, so that leads to a change of to outflow out of this warm water column. This immediately, of course, is a loss of mass. It's a loss of mass to the water column, and this loss of mass leads then to a reduction of the sea level in the adjustment process, and at the same time an inflow at the deep ocean. And then there are also, because we are on the rotating Earth, there are also rotations associated that on the northern hemisphere, of course, the flow is deflected by Coriolis, and that leads also to some kind of vorticity change in the water column. So the result of this is that you have initially, and this is the black line in the figure C, you have a change, a modification of the local pressure as a function of depth. That is 0 below the warming part because there's no mass added or removed by the warming. But then after the adjustment, there's water is lost to this particular water column, and the pressure is reduced over the entire water column by a small margin. In a Boussinesq ocean, this is different because warming in a Boussinesq ocean doesn't mean that you change the sea level height, but because you don't change the volume. Basically, by warming the ocean, you remove the mass. You remove mass. And this then immediately leads to a reduction of the pressure in the deep ocean. So then you have the pressure gradient not at the top, at the surface, but you have it at the deep ocean, and water flows in. Right? This lifts the water column, so you have a sea level rise, but it also reduces the water level in the rest of the ocean because you move water out of the ocean into this particular water column, out of the basin. And because now you have a sea level rise locally, there's again the pressure gradient also at the surface, and you have outflow. So when you compare the two images B and E, they look actually quite similar, except that the mechanism to which has produced them is different, and you have actually modified the sea level outside of this area. And this is also depicted in this figure F, where you first have a large change of pressure, delta PB 0, which comes from the warming. So you warm the ocean, you take away mass unphysically, and then the whole process starts. This leads to something like, this type of adjustment leads to so-called Goldsboro-Stommel gyres, and which is, it's an order of magnitude smaller than the direct forcing by freshwater, but still it's a circulation that you could in theory measure, and Boussinesq models do not have this circulation. So how do we include these non-Boussinesq effects now in ocean models? I mean, we have this legacy of big GCM codes, and we want to fix them, maybe, right? And there are various methods, and most of them were, some of them were constructed back then, especially this method by the group around McDougall, Greatbatch, and Liu, who reinterpreted old codes and added a little bit of time stepping to the equation of state. And then there's this other method which I will also show, and which we used back then, and which was implemented in MOM5, is that following an idea by de Zirke and Samuelson, you can exploit the similarity or the duality of the Boussinesq and non-Boussinesq equations depending on what vertical coordinate you use. I'll get into this. And then of course there are models that have been written entirely from scratch. So there's a model by Wang in pressure coordinates, and Tony Song at JPL wrote a sigma model that was entirely non-Boussinesq, and used this a lot for studies exploring GRACE data. So that's really the way to go. Recently, there has been a model that uses a non-Boussinesq algorithm, but this is not really to solve the mass issue, but really just to make the system to actually solve the system. And I would not call this a non-Boussinesq model, but there will non-Boussinesq methods are used to make it work. So now I'm going to talk a little bit about the McDougall great batch and Liu or great batch method, because there's a problem with a third problem with the non-Boussinesq models or with the Boussinesq models, and this comes from the Reynolds averaging. So here down there you have the tracer equation, and usually when we write these models, we do Reynolds average. So we replace the variables in there by the mean variable plus the fluctuation, and then average the equations. So and then add the so-called stress terms or Reynolds stress terms and parameterize those in diffusivity or viscosity terms. But if you do this with a Boussinesq model, which is the second row in the second equation here, then you end up with a divergence-free Eulerian velocity u bar that is not real. And I'm not going to go into the details of this. This will take too long. But this introduces errors in the tracer equations that are, according to McDougall et al., are on the same order of magnitude as the vertical diffusivity terms. So that's pretty serious. And what they did is they said, we just don't interpret the velocities in these ocean models as Eulerian velocity, but we interpret them as some density-weighted means. And this is now complicated to look at because these abbreviations are so ugly. But in the end, this u tilde bar, so the second thing here, is now the velocity that we use in these ocean models. We don't change anything in the code. We just interpret them or reinterpret them as these u tilde bar velocities. And then you can write your non-Boussinesq equations as down here, and the Boussinesq approximation. So you have, average density here, and then a reference density, and density average tracers, and these density average velocities. But now you can do your Boussinesq approximation, replace rho bar by rho naught, right? And when you do this, you end up with your Boussinesq equations. And it turns out that these are much more accurate. But based on this, Richard Greatbatch implemented these equations and added a time-stepping scheme to update basically use these equations in the end, and added a time-stepping scheme to the continuum equation. And what else? There was something missing here. Anyway, and then showed that this has an effect. So the dashed line here in this plot is this mean sea level, which is 0 in a Boussinesq model over a couple of years here, some 100 years or so. No, it's not 100 years. It's some 10 years, and then the solid line, the thick line, is a non-Boussinesq model where the thermal expansion is being is actually visible now. So you have you have warm in summer, it's warm, the ocean is expanded, so the sea level rises, and then in the southern hemisphere summer it is contracting, and in the northern hemisphere, and so you get lower lower sea level. So this is the Boussinesq effect. And but you see the thin line is actually the freshwater, is when you add a real freshwater to these ocean models, and then you have, of course, a mass change, and this is then reflected in the mean sea level at a much higher amplitude. Okay. This was the method of reinterpreting the variables. And there's, But there's another method, and this is based on de Zurcher and Samuelson, and they just nicely describe that if you do a change of vertical coordinate, so which doesn't have to be pressure, but can be interpreted as pressure, then your continuity equation, 2.9 here, your continuity equation can be written in the form 2.10, where now the horizontal gradient, so the nabla term, is along pressure with our p coordinate lines and not along z coordinate lines anymore. And the vertical velocity term is replaced by some d omega over dp, where omega is something like a pseudo vertical velocity. And this is nice, right? Because it looks very similar to the original equation. But the trick is now if the pressure is hydrostatic, so we make the hydrostatic assumption, then this rho zp, so this is the rho dz over dp, is just 1 over g, or minus 1 over g, and that's a constant. So that means that the time derivative in equation 2.10 vanishes, and the form of this, so it's the form of the equation, of the continuity equation, is identical to the Boussinesq form in z coordinates. And this makes it very easy to switch between, or fairly easy to switch between z and p and pressure coordinates. And this is what well, this is a bit confusing, but here you have these two sets of equations. On the left-hand side, it's the equation in z coordinate. On the right-hand side are the equations in p coordinates. Don't look at the details. I will go through this on the next slide. But the main point is that now the free surface in the z coordinate model is of course at the top of the ocean. Or the free surface variable, and you have the topography, but for the pressure model, the free surface variable is now at the bottom of the ocean. It's actually the bottom pressure anomaly, and so the coordinate system is turned upside down. That makes it a little more complicated to think about this, but in theory, it's in general, it's really the same thing. Vertical velocities are replaced by the pseudo velocities, and the pressure is replaced by some geopotential. If you do this, you can write your equations in a general r coordinate, where now everything is relative to r surfaces, and these r surfaces can be either z or p. And then this phi is either the pressure, P over rho, or it's the geopotential, depending which coordinate you are in. B is either the buoyancy, so this would be the hydrostatic equation, either the buoyancy rho over rho naught times G, or the specific volume alpha, which is basically also just 1 over rho. And both of them can be determined from the equation of state, EUS, equation of state, and then you have to make sure that for the sea surface height, or for the free surface variable r at the surface, you have to make sure that your freshwater input has the right units. So in the Z model, it's a volume unit, and in the P coordinate, it's a mass unit. So that's what this gamma does. It's just a unit conversion. So you can actually switch between these two systems within the same model code, and that makes it possible to compare the different coordinate system without too many confounders. There's still a few left. So the big problem is that the coordinate interfaces don't coincide between the P and the pressure, Z and the pressure coordinates. So that you'd have to interpolate to a common coordinate system that could introduce errors. We anticipate very small differences, so these errors could be large compared to that. So for this reason, we only compare vertically integrated fields or depth integrated fields, so like sea surface height or bottom pressure. And then there's, of course, some of these processes like the horizontal mixing is now also along Z surfaces or pressure surfaces, unless you actually rotate them. This is something which we did not do, but that makes it a little bit complicated for the comparison. Okay. Nevertheless, we can make these comparison, and we can. So in 2004, we published this paper where we used a very coarse model, 4-degree model. So these are grid cell widths of order 300 to 400, even more, 440 kilometers. So it's really a very coarse model. But it reproduces, has no CIs. It has a simple convective adjustment scheme, so no really mixed layer model. So it's really super simple, but it has a nonlinear free surface and 15 vertical levels. The nonlinear free surface is important to make the P and the Z coordinate as similar as possible. And so you get sea surface height here, or dynamic topography, the usual features with the Gulf Stream and the Kuroshio and the ACC. Everything is nice to, as far as what you expect from this type of model. And then there are now differences between, so these are long integrations, 1,000 years or so, and this is the averages over the last 100 years or so. The difference between the non-Boussinesq and the Boussinesq model in the top right panel is mainly big in the Southern Ocean, so with amplitudes of up to 3 centimeters or 4 centimeters difference. And now, since we can relax the hydrostatic approximation. I told you this in the beginning, to have the quasi-hydrostatic model, and the differences here of that approximations are a little smaller maybe, but still similar order of magnitude. So the maximum difference is on the order of 2 centimeters. Then on the bottom right panel, I compare two simulations where I changed the vertical diffusivity, so the kappa in the tracer equations, where I changed this by 1%. So instead of 5 times 10 to the minus 5 meters squared per second, I use 5.05 times 10 to the minus 5. And this is a parameter that's a tuning parameter normally, so we can modify it within ranges without having to justify this very much. But this small change gives a similar order of magnitude as the non-Boussinesq effects here for the mean sea surface. Okay. In the next, I'll compare the sea surface height variability. Now, this is a very coarse model, so you don't expect that much variability. And but there is some. And that the bottom line of this is that again, the non-Boussinesq effects are small compared to the signal, but they're still, order 10% or so. But for the quasi-hydrostatic approximation, it's the same order, if not even larger. And in the bottom right, I use, just for comparison, again, I compare two model runs where the equation of state is different. So I use different formulations of the equation of state. Both are supposed to be, correct, but one may be more accurate than the other. And again, this introduces changes on the order of the non-Boussinesq effect here for the sea surface height variability. And now the bottom pressure variability, which is maybe the most important one, because that's what Grace can measure. And again, the top left, you see the hydrostatic Boussinesq model, and the largest bottom pressure variabilities in the Southern Ocean with up to 24 centimeters. So this is pressure units converted to centimeters. So that everything, centimeters of water, basically, so that we can compare that to the sea surface height. And of course, there are now effects also in the Boussinesq and non-Boussinesq differences. Note that the color scales are not the same. So the largest values in the top left is 24 centimeters or so, and the large values in in the top right are on the order of 10 centimeters. So there are, non-negligible differences. But again, if you use the quasi-hydrostatic approximation and compare that to the hydrostatic run, it's even bigger, right? And my favorite plot is the one on the bottom right. I'm sorry. This is the difference between two runs. Now, the differences have a different sign, but that really doesn't matter. You could just change the difference, change the sign where in one run I use my surface forcing, and I perturb the surface forcing at the last digit of a double precision field. So I basically added noise to the forcing fields, and this noise is there to simulate the effect of numerical truncation that you would get if you change the compiler, for example, or change the operating system, or go from one computer to the other. But even this is even changing the compiler does this kind of thing, and you see that this type of change, random perturbation of the forcing at a very, very small 10 to the minus 16 level, has a similar effect as the non-Boussinesq. So you can look at this also in an integrated sense. I'm sorry. Here you see the blue line. Those are the projected or the estimated errors that Grace would have as a function of horizontal scale. These are spherical harmonics, if you want to know, but just imagine we have here 8,000 kilometers, 4,000, 2,600, 700, 2,200 kilometers. And the typical behavior of the Grace error model is that the errors are super small, so millimeters, right, on the very long scales, and then they become larger and larger and larger. But here they are very small. I think the actual Grace errors are even smaller than those. But that was the data that we had, and I plotted the differences between the different models that I showed you, again decomposed into scales, and you see below 4,000 or 3,000 kilometers horizontal scale, the errors are larger than what the Grace model, or the Grace data would be, and so you could actually detect this. But the non-Boussinesq effects are in green, and the quasi-hydrostatic effects are in red, and the difference to the noise is this purple color. And you see they are all the same order of magnitude. Right? So, for small scales larger than 2,000 kilometers, the errors are larger in the Grace data, and we can still, our models are good enough, maybe, right? And for long scales, the effects in the model are bigger than the Grace error, but the numerics and the details of the compiler and so on are actually as important as the physical approximations that we typically do in our ocean models. So, but this is only true for coarse resolution. And now the story may change at higher resolution. This was my conclusion back then. But for the coarse resolution models, Boussinesq and hydrostatic approximations have a similar effect on the circulation. The effects due to the numerical truncation error and unclear parameterizations, such as the equation of state and the vertical diffusivity, are also of similar magnitude. And what I found super interesting back then was that even these coarse models are super sensitive to small changes in the dynamics and forcing. That is an important conclusion for me. That goes way beyond the Boussinesq approximation. It is true for anything that we do. We have to be very, very careful with changing details. They will always change the result. Okay, so now I'm in the last 5 minutes or so that I have. I will rush through the update, when you increase the complexity in the solution, you get a slightly different answer. So now I have a higher resolution model. This is approximately 1/3 of a degree, 50 levels. There are some eddies, and there's certainly more fluctuations. We added a sea ice model also to the pressure coordinate system. We use now a common eddy parameterization scheme, the Williams and Reddy scheme, with a small coefficient because we resolve some of the eddies. And there's actually a mixed layer model, turbulent kinetic energy scheme turned on together with some other model that is not important at the moment. And you can then again compare Z versus P coordinate simulations, and the left-hand side is Z, so the Boussinesq model, on the right-hand side is the P coordinate model, which is the non-Boussinesq model. They look very similar. You have at the top the sea level, the standard deviation of the sea level, so the variability of the sea level, and at the bottom, the variability of the bottom pressure. At first sight, is not so different, but if you look at the differences in the difference plot, then you see that there are actually differences that are maybe not negligible. So especially again in the Southern Ocean, this seems to be very important. So top left is the sea level differences. Bottom left is the sea level anomaly. So the standard deviation of the sea level anomaly. That's maybe not so interesting, but the bottom right is the anomaly of the variability of the bottom pressure, and that is actually there you seem to have systematic differences with larger variability with the Boussinesq model in the lower latitudes and smaller variability in the higher latitudes. That is a bit concerning. And if you compare this now to differences to the US, the equation of state, same game as with the 4-degree model. It's again, similar order of magnitude. Maybe the Boussinesq model differences are larger. And then again, and here again, this quasi-hydrostatic approximation difference is also there, but it's maybe, again, the Boussinesq stuff might be larger. And here I also try to change the model numerics here. I didn't add noise to the equation of state, but I changed the vertical discretization, or the way that the hydrostatic balance is integrated in the vertical a little bit. And both is valid, but it's also causes differences, and the differences are actually smaller now than the Boussinesq differences here. The Boussinesq differences, and here the differences due to numerics. And so if you take a section through the Pacific Ocean, they look very similar. Again, it doesn't say much. The integration is not very long. But let's go to the interesting part, and this is the volume and mass. And here you see now the Boussinesq effect very clearly. So on the left-hand side, the sea surface height anomaly. My model simulation with this model starts with no sea ice. That's just the initial conditions. That's why in the beginning you actually lose sea surface height, because volume is being taken up by the sea ice model. The green line is minus the sea ice volume, basically. So all of the sea level drop in the volume conserving model can be accounted for by sea ice formation, and then again sea ice loss as we go on with time. The pressure coordinate model has a stronger signal, because at the same time the ocean is warming, and you have this expansion of the volume, which is not captured by the Boussinesq model. And when you look at the mass anomaly, which is similar, you see that the mass, the volume that is being taken out has a mass signal, but the warming is not being captured, so that the mass signal of the Z coordinate model here, the blue line, is wrong. Now we can apply the great batch correction that I talked about, right? I mean, this is the error really that we are making. And if I apply the great batch correction, this is super simple. You suddenly get much more accurate results. So the orange line, with the z-coordinate model, right? So on the global scale, the grad bed correction still works very well, even for this higher resolution model. And it also works on shorter time scale. So this is basically the same thing, but I look at the CSAF. I mean, before I was annual means here, but now I look at the at shorter. So I think these are 10-day or daily means that I print, and you have a short and you see that even for this for these shorter time scales, the corrected Boussinesq model and the non-Boussinesq model have very similar sea surface height anomalies. And the same is true for the mass anomaly. So the error that is in the blue line has been corrected to be almost identical to the red line, which is the correct one. So that's nice, right? So we can still use our Boussinesq models for this type of stuff, and if we do the proper correction afterwards. But there's one thing that I wanted to show you here. This is the equatorial transport across. Well, this is the volume transport or mass. I'm sorry, not the volume transport. It's the mass transport across the equator in megatons per second. That's very similar to Sverdrup. When we look at the numbers, and here it's obvious that this is caused by the surface freshwater mass flux. Basically the ITZ intertropical convergence zone moves across the equator back and forth over the season, dumping the water in the northern hemisphere and in the southern hemisphere, and then there's a flow that compensates for this across the equator, and this flow is actually being underestimated by the z-coordinate model by approximately 1 Sverdrup, and so with the pressure coordinate model, you can reproduce the mass flux to be identical to the or nearly identical to the surface freshwater flux between the two hemispheres, and but in the Z model you underestimate that. So that's basically on the regional scale. There can be corrections for this, but it becomes more and more complicated. So that was basically my everything I wanted to show. My conclusions for the second part is that this grad bed correction is still accurate even at higher resolution, but the differences between the non-Boussinesq and the Boussinesq models may be larger at higher resolution. And what's more important is they may be even systematic. But still, other uncertainties are also large, right? So I can't give you a yes or no answer to my initial question if we would need non-Boussinesq models. It definitely makes sense to use the Boussinesq models, so the mass conserving models for sea level studies. And so I showed you one case where the correction becomes more difficult, and you would actually think and work a lot if you think about corrections in other areas. But, and this is the thing that I wanted to mention, it is not, and if you use this pressure coordinate model system, it is not more expensive to run non-Boussinesq models because the code is identical. It uses the identical code. It's just the reinterpretation of the vertical coordinate. The elliptic solver that solves for the sea surface height or the bottom pressure and in one or the other cases is identical. I think even the number of iterations that it needs to converge are very similar. So there is basically no or hardly any difference in the time to solution between the Z model and the P model. And this alone would be my argument for saying use non-Boussinesq models because they're not more expensive, so there's no reason not to do this anymore. The only setback is that we have these legacy codes that use Z models, and all these parameterizations are written for Z models, so you have to translate that to pressure coordinates. And we have done this here now with the sea ice model and the vertical mixed layer model and the eddy parameterization. But of course, there are many more parameterizations that you would need to adopt. Okay, and with this, I thank you for your attention. and happy to take any questions that you may have.
Hi, Martin. Thanks for your talk, and your talk is very nice. And may I ask a very simple question?
Yes, sure.
You have shown that the non-Boussinesq effect is very obvious in sea surface height. So would non-Boussinesq have similar influence on the CS velocities?
On the sea ice velocities?
Not ocean velocities, sorry.
The ocean velocities. Well, yeah. I mean, the circulation does not change fundamentally. It does change, right? So if you look at, let's see, if you look at the mean sea level, right? So here you have differences, and this means that of course the circulation has changed a little bit. It mostly has shifted a little bit to the north here, and so that makes it different. Whether this is systematically correct or incorrect, I don't know, but it has an effect, but again, the effect is relatively small, right? And if you look, and I showed you the comparison. I showed you this comparison, right? Which is just comparing the actual fields to each other. I mean, if I only showed you the left-hand side or the right-hand side, you would not be able to tell me which one is Boussinesq and which is non-Boussinesq, would you?
Yeah, I can't.
Yeah.
So thank you.
Mm-hmm.
Hi, Martin. That's a really a nice talk. I have the question.
Okay.
The one main thing is that we use the approximation, or we don't use an approximation, is how large difference between the two models. And in your slides, you show some of them exceed maybe 20%.
Mm-hmm.
But could we draw the conclusion that this 20% is larger enough? It is physically significant, but the impact, whether the impact is significant when we do the future projection, for example, or we do the forecast.
Yeah. So I think I like this slide here. So if we talk about sea level projection, for example, with a non-Boussinesq model, that would be the red line, right? Of course, I mean, this is not a real projection. This is just a test, right? And it's a hindcast. But if you talk about the sea level rise, this would be the sea level rise in the non-Boussinesq model, and this would be the sea level rise in the Boussinesq model if you don't correct it. But we know we have this correction, right?
Yeah.
So you have to decide for yourself whether this is good enough for your study or not. I think for the personally, my personal views for the sea surface or for the sea level, global sea level studies, it's good enough, right? So we can actually work with our Z level or our Boussinesq models for quite some time. Where it is then becomes more important is the last slide that I showed, where you look into regional differences, right? And there, of course, it makes a lot of difference whether you use a Boussinesq or non-Boussinesq model. So if you think about Greenland melting, right? Then what happens is the ice mass melts and there's freshwater discharge into the ocean, but at the same time you have mass loss over Greenland, so you have less attraction, and then there are subtle differences between for the sea surface height locally, right? So actually the sea level locally would actually drop because of the mass loss, because there's less attraction. And this will be different for Boussinesq and non-Boussinesq models. And then since we actually can observe this now at a very high level of accuracy, it would be almost embarrassing to run a model that cannot reproduce this, right?
Yeah.
So I think the particular application is important.
Yeah, the physically we need that. Yes, I fully agree that. But sometimes, I mean, it's not my argument. It's just someone may argue that difference is now significant, and we can do it by some kind of the corrections and adjustment.
Yeah.
But it is not physics, but it is a practical solution. So, what's your opinion on this?
Well, again, I mean, for practicality, if you don't have, I mean, if you have your model system set up and it is Boussinesq, right, and you need to now address a question of sea level rise, then you probably would not change the model unless because you can do the proper correction. But if you're now looking into the details of this and the variability of bottom pressure or the mass distribution between two smaller basins in your ocean, then you will have a hard time with your Boussinesq model, and then you probably will have to actually do a non-Boussinesq model. My main point for non-Boussinesq models, and this is what I said at the very end, is they are not more expensive if you do it with pressure coordinates. So you could now use, I mean, you can use the what I've shown was done with the MIT GCM. You could use the MIT GCM, or you could use MOM5. I don't know, MOM6 for some reason doesn't have this, I think. I checked yesterday. But you could use models like this, and they have all this technology available, right? So I mean, you may still have to adjust small things if you want a specific parameterization, but for a general ocean circulation, you have most of the ingredients that you need already available. So, and it's not more expensive to run this. So it becomes very difficult to argue against using a non-Boussinesq model with this.
Yeah, I agree. Yeah.
Yeah.
Yes. Okay, so everyone, I think if you have any questions, you can just ask Martin directly, or you can also leave the message in the chat room. Yeah. So any questions, please?
Let's see the chat room.
So our students can ask questions directly if you are in the meeting room. Yeah, I think Martin can hear clearly.
Okay.
Hey, Martin, I got one more small questions.
Yeah.
I want to make sure that the non-Boussinesq effect will have no effect on the temperature and salinity, right? Or have very, very small influence on it.
Well, I mean the thermal properties remain the same, but if you change the circulation a little bit, right, we're talking about a small effect, then of course the temperature and salinity distributions will also change. But you're right, the effect is going to be relatively small, and we're not. I don't anticipate an entirely different circulation. It's just details that will change. In the same, in the same order of magnitude as the changes. I mean, in the smaller order of magnitude than the changes to the bottom pressure, for example. That's where the main effect is.
Yes, thank you. And I can from the figure I can see that the largest influence of the Boussinesq effect exists in the Southern Ocean, right?
Yeah. Yeah.
And from speaker, I didn't see, is there any other places that is influenced strongly by the non-Boussinesq effect?
Well, let me go back to sharing. So if you look at this here, so basically wherever you have strong currents, I mean, you also have the northern hemisphere where you have the Kuroshio and the western boundary currents, the convection areas here, right, where there's the deep water formation. Those are places where the Boussinesq approximation seems to matter. I mean, what I find intriguing is that the bottom pressure variability in the Indian Ocean is so much higher with the non-Boussinesq model, and that's something that I would like to investigate. But you're right, the strongest effects are in the Southern Ocean, but that's because these models, or maybe the system in general, is very sensitive to changes in the Southern Ocean. So whenever something changes in the model, it will always show up in the Southern Ocean first. It doesn't matter what you do, right? I mean, this is for Boussinesq, but I mean, if you change the equation of state, the largest effects is in the Southern Ocean as well, right?
Mm-hmm.
And if you change here the numerics, also the Southern Ocean is affected the most.
Yeah,
I mean, there are also other effects, but yeah. Well, it's always the Southern Ocean.
And it's very interesting to know that in the deep convection area, for example, in Greenland Sea and Atlantic Sea, there is not much influence of non-Boussinesq effect.
Well, if you look at the mixed layer depth here, this on the top right, this is also different.
Oh, okay.
But I agree. The largest effects are really in the Southern Ocean.
Yeah, so thank you.
Mm-hmm. Okay. Next time I'll come by. It's maybe easier to ask questions to someone who's there in person. I don't hear anything. Is that? Hmm?
I think there is some problem with microphone of Xinyao.
Yeah, sounds like it. So I can hear you very well, Rishi, but Xian Yao seemed to be cut off. I'll write a message.
Okay. So anyway, thank you again for your nice talk.
Yeah. Let's see what he says. By the way, Luigi, the signs next to this on the poster next to my name, are they actually my name in Chinese signs? Is that what it is?
Wait a minute. It means that senior scientist.
Okay. This is okay. Okay. Okay.
Excuse me, can you hear me?
Yeah.
Yeah, I have one simple questions. When I look at your slides, I can see that the Bosniak approximation can cause the pressure anomaly. So I want to ask whether this pressure anomaly can impact on the A mark in the Atlantic Ocean?
Ooh, that's a good question. I don't think did I compute the overturning circulation? Well, again, this is maybe so the generic answer to this is the differences, right, between the differences always are small, and the overturning circulation is a derived quantity that we look at in ocean models, and it's very hard to observe it, even though there is this rapid observation system. But I would argue that the differences that you would see are probably well below our observation accuracy that we have. I mean, there will be differences, but they will be small.
Thank you.
Yeah, the connection to China seems to be interrupted somehow. I don't hear anything. And Roger doesn't hear anything either, I guess, right?
No.
And Uru, you are actually at Geomar at the moment, right? So it's also not
It's also in German.
Yeah, I'm in German.
Okay, they can hear. Okay, that's good. Okay, what do we do now? I can't hear anything. If you type your question into the chat, I can answer that, but
I think Xinao is trying to enter the room again. So if we don't have no more questions, so maybe we can just finish the talk. And thanks for your talk, Martin. It's really nice. I'm very noticed from it. So see you.
See you. Thank you very much. Bye-bye. Bye, everyone.
Bye.